recording is in progress. So that's good. Okay. Before we get started, anybody having any connectivity issues, or if you're not able to hear me properly, this would be the time for you to let me know through the chat box, or you can speak up. Okay. Somebody's microphone is not switched off, so I'm going to do that right now. All right, I think we are all okay. All right, so if you haven't gone over the changes to the course, please do so on Piazza. I hope everybody has seen the document, actually verified it in detail on the class Piazza page. So I'm just going to bring that up to discuss a few key things for this week. So it's attached as a PDF, and I'm going to open it up just so that we can go over a few things. So I'm going to be doing the experiments and I'll share the results. Quiz 2 is going to be the Wednesday of this week. A review session led by James is going to be conducted on March 24th from 7 to 9 p.m. And he's going to send you guys an invitation to the WebEx meeting for you to join. And then the logistics about quiz 2 are detailed in this document. It will be open for a total of 9 hours, 8 a.m. to 5 p.m. And then there will obviously be the 20% LMS portion that will continue to be the case. So 80% is going to be a written take-home exam and 20% is going to be the LMS portion. Same thing applies for quiz 3. We are no longer going to have the optional quiz X during finals week. We will continue to work in groups of 2 for experiments and groups of 4 for project 3. So project 2, we are not going to make it due, and project 4 is mainly the experiment part. And because you're not doing that, um, you don't need to worry about project 4 as well. The undergraduate TAs have been assigned hours during the week where they will be hosting WebEx help sessions. This is primarily for Q&A, help with Piazza, PSpice questions, and so on. You can obviously ask questions on Piazza as well. My office hours are going to continue to be on Wednesdays from 2 to 4 on every Wednesday. And I have laid out, and this is based on student feedback, a simple protocol for our class meetings, which is to turn off microphone and camera, which I think most of you have done already. And then only when you interact with me, turn on the microphone. And if you want to ask a question, you simply pick a number in the chat box. And when I'm taking questions, I'm going to be answering those. Um, so I have a question over here. It says, is it okay that I'm in the 4 p.m.? Absolutely. So students are welcome to join either session. That is by design because of the time zones, and you might have other things going on at 4 p.m. I want to give you as much option as possible. On top of that, you um, can also view this on YouTube later on. So you have a third universal option as well. Okay. So that's as far as the last point over here I would add is the class website has been updated with all these changes. So uh, please track those changes on the class website. Okay. Questions or concerns about that? All right. So let's talk about experiment 6. What is so nice about experiment 6? What is so different? What are the new components that we are going to learn in experiment 6? The The new component that we are going to be focusing on in experiment 6 is the transistor. And I'll talk about the transistor in just a bit. Um, Before I forget, all the detailed content videos are available on the lectures YouTube channel by Professor Connor. So during this week, at any time, you should be watching those videos to get a detailed discussion on electronic switching. So what I'm going to do is going to be to start a discussion on how do you analyze a few key components that go into the switching operation. But that's it. This is going to be a limited discussion. The detailed discussion is going to be on the lectures YouTube channel, the content lectures that you usually watch. Those were developed by Professor Connor. Okay, so the transistor is what we are going to learn. And we are going to start a discussion on logic gates. Some of you might have seen this, some of you might not have, but we'll start from scratch. So why do we need a transistor? Why do we need logic gates? Why do we need to switch? Well, clearly, the goal is to convert something that has all the values in time, an analog signal. All the values in time are there. This is time. This is the x-axis, could be a voltage, could be a time, could be a current, could be any quantity. To convert this into essentially a two-level signal or a binary signal, we are going to focus on creating a binary signal. Meaning, uh, I want this to look something like probably that, right? I've made it into a two-level signal, the blue one, and I do that by probably establishing a threshold for the analog signal and saying that if the input is above the threshold, go high. If the input is below the threshold, go low. So I'm going to be trying to convert these analog signal into a binary signal, which has only two states, high and low. And by doing this, by going into a digital signal, by converting into a digital signal, there are lots and lots of advantages to system design. So there is immunity to noise, the fact that you only have to store two states as opposed to all the states. There's a lot of advantages of using digital signals as opposed to analog signals in terms of processing, in terms of memory requirements across the board. They are better. The only place where they lose out is the precision, right? Because we are giving up a few key things. So it turns out if you do this switching fast enough, you can take care of the precision as well, so you don't lose as much. Okay, so that's kind of what we will be looking at: establishing thresholds and converting through digital signals. Now, if I go down here, let's start the conversation about the transistor. So before I actually jump into the terminals of a transistor, maybe I talk about something that is very uh, real world scenario, right? So suppose there is a door, right? And there are people outside the door, and you are essentially responsible for opening and closing the door. And say this is the room that you can or cannot let people into. So, what are your options? So, how is this going to work? Because you control the door, you have the option of either opening the door or closing the door. And when you do open the door, people can go in. And when you close the door, people will not be able to go into the room, right? So we are going to take this little analogy here and apply this to transistors. Essentially, who is the control? The control is you, right? You are opening and closing the door to allow people in or not. The same principles are applied in a transistor for the extreme cases. But there's also a in-between case where the transistor works as a current amplifier, which is not discussed in this analogy. But for at least for the extreme cases, this is quite helpful to look at. How does it look like? Well, it has three terminals. Why does it have three terminals? Because you need something to control the opening and closing of the door, which in this case is the base terminal of the transistor. And you need something that is outside the door, outside the room, and something inside the room, right? So in this case, depending on how much voltage you apply on the base terminal, and that's controlled by you, current can either flow, current can flow, I can flow, or not.
Sir, we cannot hear anything from now.
Are you guys able to hear me? Okay, so I got a yes. All right. So we are back to business. Um, all right. So the last thing that we talked about, he stopped at current can flow or not. Okay. So let's go over this quickly again. There are going to be three terminals: base, collector, and emitter. And they're named so because of this. Emitter is emitting the electrons, and collector is collecting the electrons. And as you know, we talk about the direction of current in the exact opposite way to the direction of flow of electrons. So current flows from collector to emitter. However, the electrons are emitting from the emitter to the collector. And who controls whether current can flow between these two terminals or not? The base. Voltage at the base with respect to emitter is going to either allow the current to flow or not allow the current to flow. So that's kind of a very quick discussion of at least the two extreme cases of a transistor. So let's talk about the naming convention and the specific voltages. The transistor has three operating regions. So the first one is the cutoff region. And the cutoff region essentially means that the base voltage is not enough to turn the transistor on. So if I apply a base voltage with respect to the emitter to be, say, less than 0.7 volts, that is too small of a voltage, and that will not allow current to flow through, which means that you are closing the door and not allowing people to go in the room. That's your cutoff region. And the other extreme is when the voltages at the base with respect to the emitter are greater than 0.7 volts, much greater than 0.7 volts. For example, 1, 1.5, 2 volts, right? Higher voltages. If that is the case, then the transistor is said to be in the saturation region. And in that case, current can flow through. So that means that collector emitter junction is going to be a short circuit between those two. Right? So you've got less than 0.7 and greater than 0.7, but very close to 0.7 volts, just around 0.7 volts, we see another region. It's called the active region. In this particular region, the transistor works as a current amplifier. So how much ever current flows into the base, it will multiply that base current IB by a factor of 170, about 170, and that will flow through collector emitter. So IC, that is the ICE, say, collector to emitter, will be about 170 times IB. This is called the current gain, usually denoted by the letter beta. So three cases: cutoff region, saturation region, and active region. Active region is essentially a current amplification region. We don't focus on the active region that much, although we use it, we recognize it during this experiment, but our focus is going to be on the cutoff region and the saturation region, the switching parts of the transistor. All right. Questions so far about those three regions and how do we turn on and off the transistor? So if I can just make some notes over here, the transistor is on implies that uh, the transistor is in the saturation region. And obviously transistor is off implies that it is in the cutoff region. And transistor is active implies that it is in the active region. Let's see. Transistors are typically denoted by the letter Q. So Q1, Q2, Q3, and so on. Like you have R1, R2, L1, L2 for resistors and inductors. For transistors, we use the letter Q. Okay, so let's move on here. And we have two circuits in this case. Let me zoom in to one of them. This is figure A-2 in experiment 6. what we have over here is a voltage source, a DC voltage source connected to a 1 kilo ohm resistor, goes into transistor Q1, and you see how the base of the transistor is connected to the resistor here, the collector is connected to the resistor there, and the emitter is connected directly to ground, which will most likely be the case for our circuits. Emitters connect to ground. And then the other end of this resistor is connected to another voltage source of 9 volts. So let's answer a few questions. So for example, we can say how much current flows through IR1. So my goal is to find, say, IR1, and I will also try to find what is the current through IR2. Right? So I want to find these two currents in this particular example. Now, the first thing that you should notice is we will start our analysis from the base, because all that matters is whether the door is open or closed. And because this is a DC voltage, that means that there is no changing back and forth. That means the door is not opening, closing many times. It's a DC input voltage, which means that the door will either be open or be closed and continue to be so. So this voltage is 1 volt, right? And we essentially need about zero point 0.7 volts to turn the transistor on. So the base emitter junction is going to need 0.7 volts to turn on. So how much remains? 0.3 volts remains, and 0.3 volts will now appear across R1. That way we satisfy the sum of voltages in the loop to be 0. This is not going to go beyond 0.7. I only need 0.7 to turn on. Once it turns on, that's it. It saturates. It's not no longer going to go to 1, 2, 3 volts. Maybe it's going to increase a little bit, but not by much. So the rest of the voltage needs to go across IR1. And if you know the value of R1 and the voltage across R1, you can clearly calculate the current through R1, which is going to be what? 0.3 milliamps in this case. Next, we move on to the second aspect of this circuit diagram. We had enough voltage at the base of the transistor, which means that Q1 is in the saturation region. Saturation regions means it is on. If it is on, then what that means is these two terminals, collector and emitter terminals, are connected by a short circuit. So your circuit now is going to be the smaller circuit is going to be 9 volt source connected to a 1 kilo ohm resistor, short circuit, ground. Right, that is going to be your circuit now. And if that is the case, what is going to be IR2? Well, that is simply going to be 9 volts across 1 kilo ohm resistor, which means 9 milliamps. So 9 milliamps is going to flow through R2, and you have 0.3 milliamps going through R1. There is some gain in the current, but it is not um, as high as it could be in the active region. Let's see. So how much current flows through the transistor? Well, if 9 milliamps flows through the resistor R2, it is going to be the same current that flows through transistor Q1. So 9 milliamp flows through Q1. All right, so I think that's good in terms of the analysis for this diagram. Let's quickly move on to this one. Over here you have a transistor, two resistors, three resistors, voltage source, two voltage sources. So let's try to answer the question, how much current flows through IR3? In this particular I want to know how much current flows through IR3. Now, assuming this is not the case, but if you assume that Q1 is off, how much current will flow through IR3? If Q1 is off, that means your circuit, this is an open circuit now. If that is open, that means the circuit is going to be one voltage source and two resistors. So it's going to be a simple voltage divider where the voltage source is being offered a 2 kilo ohm resistor load, which means the current is going to be what, 4.5 milliamps. Only when Q1 is off. It may be the case, it may not be the case. Well, it is not the case, definitely, because the voltage is enough to turn the transistor on. But I just wanted to discuss this in case you have a voltage source V1 which is say 0.5 volts. Then that would be your answer. Now let's move on to this circuit. We have 1 volt here, which means that the transistor is on. If the transistor is on, I'm going to replace that with a short circuit. If there is a short circuit, the current, all of the current will flow through Q1, which is going to be about 9 milliamps. 9 milliamps flows through Q1. None of it will flow through, none of it will flow through IR3, because over here you have 1 kilo ohm resistance being offered, you have no resistance being offered over here. So in this case, IR3 will be 0. So these are some simple circuits that you could start looking at with this discussion. All right, let's take a moment here for questions. All right, let's move on here and talk about comparators and Schmitt triggers.
Professor Mead, someone has a question.
Yes. Explain why IR3 is 0 again. Okay. Uh, the collector and emitter are not for electron. So the collector and, let me answer one here. The collector and emitter are essentially terminals that are um, belonging to the transistor, but current could flow in and out of them. So in our case, the electrons will be emitted by the emitter and collected by the collector. But as you know, the direction of flow of current, I, is exactly the opposite to the direction of flow of electrons. So electrons go this way. Current, for our class, we have been talking about current direction is the direction of flow of holes, which is lack of electrons. So direction of flow of current is from collector to emitter. However, the electrons are going in the opposite direction. Let's answer. So that's one. Two is, how did you get 4.5 milliamps if the transistor is off? So if the transistor is off, that means that there is an open circuit over here. So let me draw that open circuit by saying there is a connection here and nothing is connected there. Right? So your circuit should look like this. Right? That's going to be the circuit. That's it. Because Q1 and rest of the circuit is out of the question. And in that case, you have a 9 volt source connected to a 1 kilo ohm resistor and another 1 kilo ohm resistor, and those are in series. So that would mean that the current I should equal 9 volts, and you're offering 2 kilo ohm resistor to that. So that should be about 4.5 milliamps. only when Q1 is off, which is not the case in this particular diagram because our input is more than 0.7 volts. So I hope I answered 2. 3 is answered. What happens if V1 is 0.7 volts? So if V1 is 0.7 volts, then we are not going to be able to comment about you are going to assume if this is 0.7, then you are going to assume that the transistor is on, but as you can see, this is going to be zero current. So the current through IR1 you will not be able to calculate. So for the purposes of this class, we are not going to talk about the exact 0.7. We will give it some little bit more or little bit less voltage so that you can analyze circuits like this. How did you know R1 drop is 0.7? So if I have 1 volt at the source, let me erase all of this now. You have 1 volt source here. This guy requires 0.7 to turn on. So the remaining voltage is not going to go. I've already opened the door. I don't need to open it wider, right? I've already done that. So the remaining voltage, what is remaining? 1 minus 0.7. Where does that go? Well, that goes across R1. So in this case, R1 is behaving as a current sensing resistor, a resistor that senses how much current flows into the transistor. So that's how I know that this is going to be 0.3. Okay, so I hope that clarifies the 4 questions. All right. Let's see. Keep going down. Comparators and Schmitt triggers. Now, this is sort of the meat of today's discussion. It is simple, but it can get complicated, especially when we start talking about Schmitt triggers. So what are we doing here? We are either comparing or we are comparing better, right? That in very, very simple terms, that's all. That's it. That's all we are doing. So how does this work? In a comparator, let me start with this. All right. So I have a circuit over here that I have laid out, and I want to answer these questions. What is the reference voltage or the threshold voltage based on this circuit diagram? What is the configuration? How do you analyze this and try to sketch given the input? So let me go into this. This is a comparator. How do I know it is a comparator? Because the voltage source, this is my input that I'm trying to compare. This is my input. The input only is being compared with one thing, one voltage. And that particular voltage in this case is 0. So the voltages that appear at pin number 3, let's call that V3, and pin number 2, let's call that V2 of the op amp will be compared. So V3 is the input and it's a AC input. So that keeps changing. And it could look like something like this, the blue guy. I've arbitrarily drawn a changing voltage, so an AC voltage. That's my V in, and I'm calling that V1 because this is labeled V1. So that's my input. I'm comparing that to whatever voltage appears on pin number 2. In this case, it happens to be 0 volts. So that is 0 volts because pin number 2 is directly connected to ground. So my reference voltage for this particular comparator is 0 volts. What is the configuration? Well, that has to do with whether the input is connected to the non-inverting terminal or the inverting terminal. And as you can see, the voltage source is connected to the non-inverting terminal of the op amp. So the configuration is going to be non-inverting. Non-inverting comparator. How does it work? Well, we are trying to compare the input to 0 volts. So this is how it works, and it is non-inverting. So I can write two statements about the analysis. One is, if V3 is greater than V2, in this case V2 is 0, so I can directly write that. If V3 is greater than 0, then V out, the output of the op amp, will saturate high. In this case, my saturation voltage is going to be the positive voltage supply, which is 5 volts in this diagram. And the second statement is, if V3 is less than 0, then V out will saturate low, negative 5 volts, because that guy is negative 5 volts. One thing to note here, V3 greater than 0, higher voltage, higher output, lower voltage, lower output. That is because of the non-inverting comparator configuration. If this was reversed, then you would get V3 greater than 0, output would have been negative 5, and vice versa. So in this case, input and output are going to be in phase because of the non-inverting configuration. All right, I've written up these two statements. Now I'm just going to use these two statements to complete the sketch below. So what we have over here in blue is the input signal, and as you can see, there are some high peaks and troughs, but also very small changes close to 0. This is 0 volts here, and x-axis is time, y-axis is voltage. So I've arbitrarily chosen an input signal which changes with time for my input signal V1, and I'm trying to sketch my output of this comparator based on the two um, statements that I've written up just now. So let's see. If V3 is what? V3 is essentially the input, as you can see. So this is it. The blue guy is V3. If V3 is greater than 0, output is 5 volts. So in that case, over here V3 is greater than 0, so the output should be 5 volts here. Let me take a thicker line. And when V3 goes below 0, we said output should go negative 5. And then I'm going to quickly complete this one. Again, it will switch again over here. Switch again over there. Switch again over there. Switch again over there. All I'm doing is comparing the input, the blue line, with 0 volts because my threshold is 0, and I'm jumping up and down in phase with the input. It's going to remain over there until there. Goes down to 5 volts. And so on. So based on these two statements, we have sketched the output of the comparator using the red line. That's going to be my output voltage, V out. Did we make this binary signal? So we could just simply convert it an analog signal, the blue one, to a digital signal in the red one. So we made it binary, having two levels, low and high. Now, one problem that I hope you recognize over here is when it was a really solid high level and really solid low level, you probably intended that it be a high level at the output and low level at the output. However, if you focus on this particular region here, my guess is that this could also be because of noise. If you focus over here, that input is changing very small voltages, right? So it's not a very big change, and it is around zero. So that's a very good representation of noise. And the big problem with a comparator is that it reacts to noise. We don't want to react to noise. We want to remove this problem where the output jumps up and down because of very small changes close to the threshold level, which could be due to noise, which could be due to like something that you did not desire, but it was something that happened in your design because of thermal noise or noise coming from a different source. So you don't want that to happen. You want something that ignores really small changes in the input that are close to zero. And hence we talk about the Schmitt trigger later on. Questions about the comparator? All right. Let's do another one, but not completely. We'll just give it a start. Here you have another comparator. How do I know it's a comparator? Because input is being compared with 1 volt. So still non-inverting comparator because input is connected to the non-inverting input of the op amp. I just now said the reference voltage or the threshold voltage is going to be 1 volt. So the voltage level to which we compare the input. Earlier it was 0, now it is 1 volt because that's 1 volt. The configuration is a non-inverting comparator, and the statements for analysis. If input Vin is greater than 1 volt, then output equals 5 volts. Similarly, when input is less than 1 volt, output is going to be negative 5 volts. Using these two statements, you can sketch a similar diagram to this. However, your threshold is now going to be slightly up. So it means that it might be over here. So you might not react to noise that much. However, if your signal is offset, then you continue to have that problem. Okay. So so the rest of this, you guys probably see how to do that. Let's move on to the Schmitt trigger. So for the Schmitt trigger, okay, well, let me leave this. The circuit diagram is going to be slightly different. Now what we have is an input voltage going into the inverting terminal. So this is going to be an inverting Schmitt trigger configuration. Your DC supplies are plus and minus 5 volts. So those are going to be the saturation levels for the output. So output can either go +5 or -5 in this case. And we are comparing the input V1 to an input, another level, which you have to work out. It's not a standard DC voltage source as you had in the case of comparator. Let's call this V3. That particular voltage, which is connected to that terminal, non-inverting terminal over here, I'm just calling that V3. The discussion that follows is not that trivial, so I hope you guys listen in and ask as many questions as possible. And this is your input. This is my output that I'm trying to sketch. So what can we say about V3? I'm going to need to find V3 because I'm comparing the input with that particular voltage V3. So I need to find V3. How do I find that out? Well, this output V out is essentially divided between R4 and R5, and V3 is essentially the voltage across R5. So let me write that down. V out is divided between R4 and R5, and the second statement is V3 is voltage across R5. So how do I find that out? Well, for V3 is very simple, right? V3, because of voltage division rule that you have seen so many times, we simply say V3 equals V out multiplied by R5 divided by R4 plus R5. You guys have seen this before. And what do you know about V out? Well, output can either go +5 or -5. It can saturate either high or low depending on how things compare. So you know that those are going to be your two options. You already know the values of R4 and R5. So we can find out the two values for V3 in this case. So let's see, V3 is going to be plus and minus 5, that's V out, times 1K divided by 1K plus 4K, because R5 and R4 are 1 and 4K each. So what does that simplify to? That should simplify to plus and minus 1 volt. And we also noted that this configuration is an inverting configuration because the input was connected to the inverting terminal of the op amp. So based on this, by the way, the reference is over here. We said the reference voltage is 0 volts because that is 0 volts. You could change that particular voltage as we will see in the next example. Now coming to this, V3, we calculated that to be plus and minus 1 volt. Now our analysis statements are going to look something like this. If input V1 is greater than V3, then the output will saturate low, which in this case is -5. If V1 is less than V3, then the output will saturate high because it's inverting to plus 5 volts. And we already found out that V3 was plus and minus 1. So using these two statements, we can actually do that sketching exercise again. So we have the same input, and we are going to use those two statements to find out the output. So what do you have here? we have the two statements are V in greater than 1 volt implies V out is going to equal negative 5 volts. And the other statement is V in is less than 1 volt. That implies V out is going to saturate high to plus 5 volts. So how does that look like for our in this same input? What I like to do is first I like to highlight the thresholds on my plot. So I'm going to say, let's suppose that this is 1 volt over here, and this is say negative 1 volt over here. It might not be to scale. I'm just sketching, um, uh, uh, an approximate line of plus and minus 1 volt. Say this is 1 volt, this is negative 1 volt. So if that is the case, I'm still going to try to sketch my output in red. So what is going to happen? Over here is when the input crosses 1 volt and goes above that. So when it does that, the output will saturate low. So over here is when it will jump down. And for how long will it stay low? When the input goes below negative 1. And then once it goes below negative 1, it's going to shoot up to plus 5. Until when does it stay up? So it's coming from here. All right. Until when does it stay up? It's going to stay up until the input crosses plus volt again, plus 1 volt again, and go above that. So that time it's going to go low. And then if the input goes below negative 1, it's going to saturate high again. And then that's it. It stays there because over there it doesn't even. So now if you can see, the noise was here, but we didn't react to it. It stayed high during that time. We were still able to convert an analog signal to a binary signal, 2 levels, but because we had 2 thresholds, the reason why this worked so well is because we had 2 thresholds, an upper threshold level, and a lower threshold. So hysteresis is simply upper threshold level minus lower threshold level. In this case, it would be 2 volts. 1 minus 1. So we are able to ignore noise that is close to 0, but below plus and minus 1 volts. Questions about the analysis of a Schmitt trigger with 0 reference? When you're comparing input, are you comparing it to the voltage reference? Yes. So I'm comparing it to the 1 volt and the minus 1 volt. However, I'm not comparing to this reference voltage. That reference voltage actually means that you have connected 0 volts at the end of this R5 resistor. And in the next circuit that we are going to analyze, we will see that you could make this different. Meaning, by having thresholds plus and minus 1, I should write -1 here. If having thresholds plus and -1, as you can see, they are equal on both sides. Well, the question is, can you make them different on the positive side and different on the negative side? Yes, you can. And you can do that by attaching another voltage source at this point. And we will see that in the next circuit diagram, and we are calling that as Vref over here. I hope that clears up a bit. So the thresholds need to be calculated. This Vref is essentially meaning that you have connected a ground 0 volts at the end of this R5 resistor. Well, this will clear this up. If you look at this new circuit over here, what is Vref going to be? Well, Vref in this case is going to be 1 volt because I've connected a 1 volt supply to the end of that R5 resistor. Earlier it was ground. So my Vref became 1 volt. Is my upper threshold, lower threshold 1 volt? No, I don't know yet. I need to calculate that out. So let's do that calculation. You still have those same values, right? You are comparing, so it's still a inverting configuration here. We still need to find out V3. Let's call this V3. This is still V out. So a lot of this are going to be different, the same, but there are going to be few key things, and they are very, very crucial, that are going to be different. So what should I write about V3? Earlier, I said V3 was the voltage across R5. Is that going to still be the case? Is V3 the voltage across R5? Or is V3 the voltage across R5 plus 1 volt? All voltages are measured with respect to the ground. So V3 should be voltage across R5 plus 1 volt, or Vref in this case. V3 is voltage across R5 plus Vref. Over here we attached a 1 volt source, so VR5 plus 1 volt. So question 7 says, is Vref just the voltage source connected to the terminal 3 on the op amp? It is the voltage source that is connected to the end of that resistor. Yes. Let's see. So I hope that you guys agree with this statement here. V3 voltage at this point is voltage across R5 plus 1 volt. Next, how is V out going to be divided between R4 and R5? I need an equation for R5, VR5. So on this end, I have, what is the voltage here? On the blue, that's going to be V out. And on this end of R5, the voltage is 1 volt, right? So between those 2 points though, what is the voltage? Well, that is going to be V out minus 1 volt. So earlier V out was getting split between R4 and R5. In this case, V out minus 1 volt is being split between R4 and R5. I hope you guys see that difference. So in order for me to calculate VR5, I'm going to say VR5 is equal to that voltage multiplied by R5 divided by R4 plus R5. Next, what could be V out? Well, V out can either saturate high or low. In this case, we have plus and minus 5 volt. So V out is plus and minus 5. R4 and R5 are available. So this is 1K, 1K, and 4K. So we can find out VR5. So essentially my goal is going to be to substitute this in here and then substitute R5 in there and find V3. So what is V3 going to be? Level, what is VR5 going to be? VR5 is going to equal plus and minus 5 minus 1 times 1 over 5. That is going to equal two voltages. Either it could be 4 divided by 5 or negative 6 divided by 5, negative 1.2. These are both going to be in volts. Question 8 is, do you mean R4 is 4K and R5 is 1K? Yes, I mean yes. R4 is 4K and R5 is 1K, yes. I see what happened there. Thank you. Although it doesn't make any changes to the other steps. Let's see. I got VR5 to be that. So let me write this as 0.8. So I got two values for VR5 depending on how it saturates, high or low. Now V3 is going to equal VR5 plus 1 volt. So that is going to be either 1.8 volts or negative 0.2 volts. So these two are going to be your new upper threshold and lower threshold levels. The hysteresis is still 2 volts. However, your upper threshold level became 1.8, your lower threshold level became negative 0.2. So by having this additional voltage source over here, you can make the two thresholds different values. Earlier they were just one and plus and minus 1. Now they are different values on either side. And if you know these two, so essentially you can come up with your analysis statements. What is the analysis statement going to be? You can say V in greater than 1.8 volts. That implies V out is going to go low, negative 5 volts. And the other statement is going to be V in less than lower threshold, negative 0.2. That implies V out is going to saturate high, 5 volts. So using these two statements, you can do another sketch of voltages. Question 9 is V3 always the threshold limit? Yes, V3 will always be the threshold. Whatever voltages you have at the input of the op amp, those are the ones that get compared. 2 is the input, 3 is V3. So we are comparing input to voltage at V3. All right. I think that's about it in terms of comparators and Schmitt triggers. We'll do the logic gates on Thursday. I think it is time for me to move on to the experiment. So when I went and looked at the complete experiment 3, it looked to me like the only experiment in which you have to build a circuit is the last one. Oh, maybe I talk about this. The symbol over here, right? This is part C4 of experiment 6. That particular symbol is of an inverter. Inverter essentially means if a low level goes in, a high level comes out, a high level goes in, a low level comes out. So it's like the comparator, but in inverting configuration. However, this guy is the Schmitt trigger in the inverting configuration. And that particular symbol over there tells you that it has two threshold levels. So the symbol itself says Schmitt trigger. So let me just write that down over here. This is Schmitt trigger inverter. And this is going to be a comparator inverter. Both are inverting. So high level goes in, low level comes out for both of them. Transistors are there, and then the rest of it are going to be the same. Let's see. So you guys can work on the PSPI simulations as a group. So saying that it looks to me that part A, part B, and part C don't have any sort of circuit building exercise for experiment 6. The only thing that we need to build is this little guy here, part D, figure D-42. So I'm going to take a few minutes to set this up. Right now it is 9:10. What we'll do is we will say take a 5-minute, or well, we can take a 10-minute break. Let's take a 10-minute break. So it's 9:10 right now. Let's come back at 9:20. By that time I would have set everything up. You guys can grab some coffee or breakfast, or dinner, depending on where you are, and be back in 10 minutes. 9:20 is when I will be back. I need some time to set everything up, and then we will do the experiment.
I joined just in time for him to leave.
Was it?
Perfect. Perfect.
So I'm going to leave the meeting open